Priyanka, you are not audible. Sir, I think Priyanka have some network issue.
So next I invite Mr. Abubakar P. Assistant Professor, Department of Mathematics, Government Engineering College, Palakkad.
Is that presentation tab is enabled? Hello?
Excuse me?
Hello?
Hello? Pardon?
Is the presentation tab is enabled?
No, it's not visible.
I mean, the presentation tab is enabled, right? I couldn't see that. I couldn't present my presentation.
I just enabled. Abu, please leave the meeting and rejoin.
Let me see again.
So next I invite Miss Jinsi Poli, Research Scholar, Department of Mathematics, St. Thomas College, Thrissur.
Good evening, all. Am I audible?
Yes, Jinsi.
Is my slide visible?
Yes.
Good evening, all. Myself, I'm Jinsi Polly, Research Scholar, Department of Mathematics, St. Thomas College, Autonomous Thrissur. Today, I would like to review a paper titled Non-Singular Metrics as Private Key on Elgamal Cryptosystem. This is the way in which I would like to structure my presentation. First, introduction, key generation, encryption, decryption, analysis, conclusion, and references. Cryptography is the practice and study of techniques through which we can communicate securely. More generally, cryptography is about constructing and analyzing protocols that prevent third party or public from reading private messages. Modern cryptography exists at the intersection of the disciplines of mathematics, computer science, information security, electrical engineering, digital designing process, physics, and others. Core concepts related to information security are also central to cryptography. Practical applications of cryptography include electronic commerce, chip-based payment cards, digital currency, computer passwords, and military communications. As we know, there are two types of crypto systems. One is symmetric and other is asymmetric. In symmetric systems, the only ones know until the 1970s. The same secret key is used for encryption and decryption also. Data manipulation in symmetric systems is integers are usually form commutative groups or rings. Therefore, experts develop public key crypto system based on the concept of metrics and non-commutative ring decomposition problem in the near ring, quasi-polynomial or non-commutative group and non-commutative division semirings. The traditional Elgamal crypto system uses the complexity of discrete logarithmic equation, that is y equal to g raised to x mod p, where g is an integer and they publish public key as YGP and private key as X. Through this presentation, I would like to discuss about how invertible metrics can influence Elgamal crypto system, published by Max Rizal on the paper titled Non-Singular Metrics as Private Key on Elgamal crypto system and published in Journal of Physics. He uses the matrix G, replace the integer G by matrix G and resulting public key as YGP, where Y and G are matrix and X is an integer. This is the difference from the traditional discrete logarithm problem on in integers, and this is for the matrix. This is the key generation process. As we know, this is a public key crypto systems. The sender and receiver both are creating keys. So for recipient, suppose Bob is the recipient. Bob select a 3x2 matrix. With the help of this matrix, he create a 4x4 matrix using this equation. He placed G 3x2 here and a null matrix of order 2x2 and null matrix 1x2 order and identity matrix of 2x2 order. And choose any integer X randomly and forms another 4x4 matrix Y by powering G, for by powering G using X. Both choose another 2 by 4 matrix, called it as S, and he published the public key, his public key X Y 4 by 4 and S 2 by 4, and kept private key secretly G 3 by 2. Okay. Then suppose Alice be the center. She choose a 4 by 3 matrix, namely K, and a 2 by 2 matrix H, and forms H 4 by 4 like H 2 by 2, null matrix 2 by 2, null matrix 2 by 2, and identity matrix 2 by 2. She calculate a new matrix T of order 4 by 3 using this equation H into Y into K. So H2 by 2 is her private key, and K and T are her public key. Bob also calculate P2 by 2 using the Alice public key, using her public key T, S, T, G, and sends to Alice. This is the sorry. This is the encryption process. Alice calculate M2 by 2 by R is the message she wants to communicate. So she calculate H into P into M2 M. Also she calculate H into S into H2 by 2 into S2 by 4 into H4 by 4, where H2 by 2 is her private key, and H4 by 4 is her public key, and send Q and U to Bob. Then we move to the decryption process. Bob forms X equal to U into Y into K into G and calculate its inverse. And to read the message M2 by 2 by R, he calculate X inverse into Q2 by R. Okay, then we get M2 by R. He can read the message. The advantage of the matrix as private key in the proposed LCAML crypto system. The traditional LCAML crypto system applied sorry. The traditional LCAML crypto system applied discrete logarithmic equation y equal to g raised to x mod p with x as private key, works on the prime number p and generated g over mod p. Thus, the system strength depends on the selection of large prime p. The brute force attack takes a long time. The LCAML crypto system works on general linear groups, namely matrix equation y equal to g raised to x mod p serves as the discrete logarithm problem on GLN FP, where x is a private key. Note that the key is a matrix, resulting in more complex ciphertext randomization. This crypto system also still relies on the selecting a large prime p. The strength of the traditional LCAML system and its improvements lies in the difficulty of solving discrete logarithms. Meanwhile, the power of the proposed LCAML crypto system lies on the complexity of factoring the matrix G from the equation y equal to g raised to x mod p. If we are given y equal to g raised to 100 mod 11 equal to the matrix 7, 3, 10, 6, but we cannot find the matrix G. This is the complexity of finding matrix from the equation g raised to x. Okay. Another advantage of the proposed LCAML crypto system lies in selecting the matrix G. Note that G is a matrix, so the plain text must also be matrix of the same size. Thus, the resulting cipher is the result of multiplying key matrix G and a plain text, so that the plain text randomization become more complicated and more resistant to chosen plain text attacks. In this study, the LCAML crypto system using a matrix as the private key, the resulting system still working on a matrix of a specific size. The results shows that we can modify the key generating algorithms, encryption and decryption algorithms, so that the proposed system can work. These are the references I used. Thank you.
Okay. Nice presentation, Jinsi. Please take the slide 11. Jinsi, please.
Okay, sir.
Slide 11.
Sir,
Which operation is here? S2 form? In this equation, which operation?
normal matrix multiplication, sir.
Multiplication.
Yeah.
Yeah. Then next slide.
Here also, all the operation we are done here is usual matrix multiplication.
Usual multiplication.
Yeah.
Okay. Any queries from the audience? Any questions? Okay, very good, Jinsi. Go to next presentation.
Thank you, sir.
Sir, am I audible?
Audible. Yes.
Okay. Let me go to the presentation. Yeah.
Okay.
Myself, Mr. Abubakar, working as an assistant professor, Department of Mathematics, Government Engineering College, Palakkad. My title of the paper is Prerequisites for Cryptographic Primitives on Many Valued Logic. We have the binary and non-binary crypto primitives. That is, binary crypto primitives is that is working on binary numbers, and non-binary means it's working on ternary or quaternary like that. So for a binary, in most of the cryptographic block ciphers, Boolean ciphers. So these Boolean functions are gives output 0 or 1, and we know the modern computers are working on the binary numbers, so that the algorithm, the current algorithms are all working in binary numbers, or the
Excuse me,
components are Boolean
Abubakar.
functions.
Excuse me, Abubakar, your voice is breaking.
Yeah. Okay. Just 1 minute. Now is it okay?
Yes, but there is an echo.
Okay. What about now? Is it okay?
Okay.
Now, what is the role of functions of many valued logic in cryptography? You see, in order to design cryptographic primitives, we must have a clear-cut knowledge about functions of valued logic, which is the component of such systems. Since you know the right now, binary become computation efficiency of the quantum computation is there. So those algorithms are questioned. So one of the important characteristics of primitive or many-valued logic is the digital data. This is one of the important things that why we are using, why we have to go for many-valued logic. We can represent the data in a compact manner. Suppose that if we have a data like this, I mean 10010. This is a binary data. It is 18 in binary. It's a digit 18 can be represented as 10010 in binary. The same number can be represented as 200. That is, with 3 digits we can represent. So that what I'm telling is the data can be represented in a compact manner. This is one of the most advantage of using many-valued logic function. Now, in order to attack an algorithm, the attacker is not constrained with a way of representation of algorithm. So we know that in the modern cryptographic algorithm like AES, BES, that can be represented using quaternary the cryptanalytic method based on those many-valued logic representation as well. So there is a possibility of developing such cryptanalytic technique even for the binary algorithms as well. Now, the data representation is an important matter of any function, even if it is a Boolean. The representation is truth. This is this line shows the truth table representation of a function. It is suppose that if it is a function of n-valued logic, p-valued logic, then it can be represented as a truth table like this. And polarity truth table is omega raised to f of 000 and so on, and where the omega is the pth root of unity. Then another important representation is Reed-Muller transform, or we can also say that it is a algebraic normal form. It is the multivariate representation of a function, and this a, I1, I2, etc., In that we call as the Reed-Muller transform coefficient or algebraic normal form coefficient as well. Now, I told you that when we are designing a cryptographic algorithm, we must have a clear-cut knowledge about the component and the cryptographic properties of those components as well. So I'm going to explain how we some cryptographic functions of any valued logic. These are the properties or characteristics that I'm explaining. Strict avalanche criterion, non-linearity, degree, and correlation immunity. These are the very important characteristics of a cryptographic function. So propagation criterion of strict avalanche criterion, we know that strict avalanche criterion how the output is changed when the state of those things are strict avalanche criterion. So suppose that logic, then it's the strict avalanche of the function is given by derivative of a function is given by du of x plus 2u. The operation is on mod q. Suppose that f is a function of 3-valued logic. Here the function f dash, it is given as a function of 3-valued logic. So this is the truth table representation of that function. Then the derivative of that function is given in that table. Now you can see this is derivative of that function when the derivative is 0, 1, and 0. We have taken the derivative at each vector which have weight 1. Weight means the number of non-zero vector in that, I mean, non-zero in that vector. So here you can see that here's a minus represented 1 and plus represented 2. So you can see that this in this derivative, the 0, minus, plus are uniformly distributed. If it is uniformly distributed, we can say that this function criterion. Method the criterion, I mean criterion both even if it is Boolean or non-binary or many-valued logic function, it is very important. This non-linearity property is very important. It measures the distance from the linear function. How far this function is from the approximate linear function. That's what it measures. So for a Boolean function, the nonlinearity can be computed using Walsh transform. The Walsh transform is given by the of u equals over x comes to Vn minus 1 raised to f of x plus inner product of ux. This represents the inner product of that u and x. Now, for a few-valued or for a many-valued logic function, it can be calculated using Bellingen-Christensen, a transform called Bellingen-Christensen transform, and the coefficient of that Bellingen-Christensen transform can be computed using that function given in equation number 4. Now, this operation can be performed using a matrix called Bellingen-Christensen. For a ternary in ternary logic, this matrix is given by the this matrix, and where V3 is given by this matrix. We can find the matrix using a recurrence relation. This recurrence relation is given over here. Now, for the computation of the coefficient of Bellingen-Christensen transform, we need to transform this matrix and the given function to another form, into a complex form using the transformation given by 0, 1, 2, etc. p minus 1 is transformed to these vectors, these numbers. Then the coefficients can be computed using the expression given in equation number 5. Now, once it is calculated, then the nonlinearity can be computed using the expression given in equation number 6. For a if it is a binary valued function, it can be it can be calculated using the expression p raised to n minus 1 by 2 into maximum of u belongs to Vn wf of u. For a binary function, it is calculated using Walsh transform, and for a non-binary function, it can be computed using Bellingen-Christensen transform as well. Now, this is the Bellingen-Christensen matrix for quaternary functions. This is also, we can calculate the matrix of any order using this recurrence relation. Now, Reed-Muller transform coefficient and algebraic degree. I told you that the Reed-Muller transform or algebraic normal form is the bivariate representation of a given function. Then this is that representation, and here ai1, ai2, etc. ain is known as the Reed-Muller transform coefficient, and this coefficient will determine the rank of the matrix as well. The degree of the algebraic degree of that function. So these coefficients can be computed using this matrix, using the expression a equal to f into
rp raised to n. Now, as usual, in the previous slide, this is also can be computed using the recurrence relation. Now, another important characteristic of a cryptographic function is correlation immunity. We know that a function is correlation immune if it is resistant against correlation attack. Now, I am going to explain the correlation immunity of a function in terms of its subfunctions. So let f of x be a Boolean function and x1, x2, etc., xn are independent and uniformly distributed random variable, and the function f of x1, x2, etc., xn, where xi takes any values from 0 to p minus 1. Then we say that this is mth order correlation immune if f of x1, x2, etc., xn is independent of any set of m of its input variables x1, x2, etc., xn. Now, a subfunction is nothing but a subfunction of a Boolean function. F is obtained from f by inserting constant value 0 or 1 for some of its variables. Now, we say that a Boolean function is mth order correlation immune if weight of f dash is equal to weight of f divided by 2 raised to m. Then if it satisfies this condition, we say that Boolean function is immune. And the correlation immunity can be also defined using the Walsh transform. We say that f is a function, f is correlation immune if the vectors with weight less than or equal to. Now, first of all, the correlation in terms of subfunction, need to know subfunction q-valued function. Then a subfunction of a q-valued function, f is the function f dash that derived from f by inserting constant values from the set fq. So fq equal to 0, 1, 2, etc., q minus 1 for some of its variables. Now, we are defining the correlation immunity in terms of imbalance of a function. So imbalance of a q-valued function is the absolute value of the first coefficient of the Wellingen-Christensen transform. That is the absolute value of the sum of component-wise product of the function by the sequence e raised to i0, e raised to i0, etc., e raised to i0. That is 1, 1, etc., 1. Now, the imbalance of a function, imbalance of a q-valued function can be computed using the expression given in 6. Now, we say that a function f is a q is relation if if the all the derivatives is having, all its subfunction is having that imbalance del f divided by q raised to m. That is, del f dash is equal to del f divided by q raised to m. Now, we say that a function is resilient if it is a correlation immune and balanced function we call as resilient function. So this is some of the important characteristic of a function of many valued logic that we need to know in order to design or in order to design a cryptographic algorithm based on many valued logic. So there is a there is a hope for those algorithms since this quantum computation is working, is developing, where the states of the matrix, states of the represent is obtained from the orientation of the photons. So we can represent 0, 1, 2 as well. So there is a possibility of developing such an algorithm as well. I think there is an algorithm that is working on a ternary number system that is developed by an Ukrainian researcher named Adam Sokolov as well. Now, this is the end of my paper. So if you have any question, you can ask.
Okay. Avoga, some technical issues. Nice presentation. One or two questions.
Okay.
In SAC, mode Q, you can apply mode Q. What is Q? Is a prime or prime power?
Sir, it is a Q. If it is a Q-valued logic function, then it is mode Q operation. We perform mode Q operation. For ternary, it is mode 3.
My question is, Q is a prime number?
No, not necessarily.
Not necessary. Okay.
Yeah.
Thank you. Then one more question. How can we evaluate the correlation immunity of a Boolean function? I have no doubt.
Sir, for a Boolean function, it can be calculated using the weight of that function. I mean, here I have given an explanation using the subfunction of a subfunction obtained by substituting 0 or 1 in some places. Means if you are checking the correlation immunity of mth order, then we are giving constants at m positions. So then the function obtained we call as subfunction, and based on that function we can calculate the correlation immunity.
Okay. Any other queries, audience? Okay, nice presentation, Walker. Head on. Thank you very much.
Next, I invite Ms. Priyanka, Research Scholar, Department of Mathematics and Statistics, CCS HAU.
Good evening, ma'am.
Good evening.
I am Priyanka, Research Scholar from CCS HAU Hisar. Today, I am presenting on quantum secret sharing scheme. My slide is visible.
Yeah. Okay.
No. These are the contents: introduction, history of the quantum cryptographic schemes, proposed quantum encryption scheme, verification of the scheme, security and sensitivity analysis, summary and conclusion. In quantum cryptography, the security of quantum cryptographic system is based on the laws of the quantum physics rather than mathematical assumptions. This enables us to design secure systems even in the presence of an eavesdropper. An important and interesting result of quantum mechanics that makes quantum cryptography work is the no-cloning theorem, which states that no one can make an exact copy of an unknown quantum state. This restricts an eavesdropper who intercept the encrypted message. Since making a copy of the message and send it to the intended party is not possible, secret sharing scheme allows the dealer to store the secret among a group of participants, and a sufficient number of participants combine their share to reconstruct the secret. Now there is history of quantum cryptographic schemes. Shamir et al. Introduced a key management scheme for quantum cryptographic systems. There are many algorithms which are based on quantum computing, such as Shor's algorithm, Dutch algorithm, and Grover's algorithm. There are cryptography has concepts like quantum key distribution, quantum secure communication, and quantum digital signature. Hillary et al. Introduced the first quantum secret sharing scheme using GSZ states to create shares for different participants. Carlson et al. Presented MN scheme using the multi-particle entanglement measurement. Zhang et al. Presented concepts of unitary transformation and multi-party measurement results to reconstruct the secret without using entanglement. Now, the scheme proposed by Yang et al. Used quantum Fourier transformation for generating the secret shares. Quinn et al. Proposed secret sharing scheme using QFT and generalized Pauli operators and verified this scheme. Song et al. Introduced a scheme secret sharing scheme of classical information using QFT. Pauli operators and C-NOT gates. Masardi proposed a scheme based on monotone span program to generate shares. Now there is a quantum secret sharing scheme using Hadamard basis based on entanglement and sequential measurement. This is a secret sharing protocol. This protocol describes a 3-3 quantum secret sharing scheme where all the shareholders need to collude for reconstructing the original secret. In this scheme, there is a dealer and three participants, among which dealer D wants to share a secret. All the three participants, P1, P2, P3, has 2 qubits each. P1 participant has a qubit 1, 4, P2 has qubits 2, 6, and P3 has qubit 3, 5. Now dealer D uses any of the combined state involving alpha plus, alpha minus, beta plus, and beta minus. Alpha plus, these are the basis states. Now dealer D construct a product state using these basis state. Let the dealer construct a state alpha plus 1, 2, alpha plus 3, 4, and alpha plus 5, 6. Dealer has 4 unitary operators: X, identity, X operator, iota Y, and Z. There is a bit string also associated with each of these operators, like this: I1 equals to 0, 0. This means I1 means the operator identity is acting on the qubit 1, and I4 means the identity operator is acting on the qubit 4. Similarly, there are other operators. The overall implementation of the proposed protocol is carried out in the following steps. The dealer decides to alter the particles of P1, that is 1, 4, and he also decides to operate the Z gate on the particle 1. Thereby, the resulting state will be side dash. Here, the minus will be changed by plus when Z gate is applied. Now, dealer sends this state side dash to P1, who decides to measure his share of the entangled particle, that is 1, 4, by using any of the 4 basis element. If P1 uses alpha plus 1, 4, then the resultant system will be collapsed into the state collapsed into the state obtained in equation 5, that is half beta plus 2, 3, and alpha plus 5, 6. The particle 5, 5th, and 6th are unaltered since the measurement affects qubits 1, 4, and 2, 3 only. The qubit held by P2 and P3 are 2, 6, and 3, 5 respectively. These qubits can be rearranged by swapping their places. We take equation 5th again and multiply these terms and taking the qubits of participant P2 and P3 together. Now putting the values of minus plus 2, 6 from the original basis states, we obtain the equation 7. Similarly, the participant P2 and P3 announce their measurements and obtain their shares of the secret. Now the reconstruction of the secret is reconstructed by the parties when each user uses the correct information. We show the reconstruction result of the particular cases. There are some information which is publicly known, which is the product state created by the dealer D, the qubits operated by D, measurement of the participant P1. The participants P2 and P3, they announces their measurements, say alpha plus 2, 6 and beta plus 3, 5. Then the combined state of P2 and P3 is gamma. And again, multiplying these terms and substituting the values of these terms from the basis states, we obtain the equation number 6. Equation number 8. Now, since they know that the qubit pair 5, 6 was never tampered with Hence, the state of qubit 5,6 should be alpha plus 5,6, which correspond to only beta plus 2,3, which is the third term in the equation number 8. Hence, the current state of the qubit is beta plus 2,3 and alpha plus 5,6. At this step, the information about the measurement result of P1, that is alpha plus 1,4, then is used. Then combining the result of participant P1, we obtain the equation number 10. At this point, P2 and P3 make use of the announcement that D made about the qubit being transformed. D altered qubit 1. Then they both know that qubit 3, 4 were not affected. They would be in the state alpha plus 3, 4, which is also the third term in the equation number 10. From this, we obtain psi as beta plus 1 to alpha plus 3, 4, alpha plus 5, 6. Now, comparing the state obtained in 11 with the original shared state, alpha plus 1 to alpha plus 3, 4, alpha plus 5, 6, we observe that there is only one term, beta plus 1, 2, which was replaced, and this is obtained by operating Z1 on alpha plus 1, 2. So according to already agreed protocol, they share the string 10, since the operator Z1 correspond to 10 according to the equation 2. Now there is security analysis. There are here we will see that if any one of the participants or the dealer share wrong information, then secret cannot be reconstructed. D's announcement about the product state psi is crucial. Suppose D shares the state psi, which is alpha minus 1 to alpha minus 3, 4, alpha minus 5, 6, and he announced that he shares the state phi, which is alpha plus 1 to alpha plus 3, 4, alpha plus 5, 6. If D wanted to share a bit string 0, 0, therefore he used the identity operator. If P2 and P3 make a measurement alpha plus 2, 6, beta plus 3, 5 using the state phi, and both the participant use D's information regarding the shared product state phi. They use information about measurement result of the participant P1, which was alpha plus 1, 4, and they conclude that the operation Z is operated, which is incorrect because dealer D has shared a wrong state. For the correct reconstruction of the secret, D's announcement about the qubit being transformed is also crucial. Suppose D transformed the fourth qubit and he did not announce this information, then even if the participant P2, P3 and P1, P2 and P3 have the information about the shared product state, they would not be able to reconstruct the secret. For instance, if P2 and P3 measures alpha plus 2, 6, beta plus 3, 5, then using information given by D on the shared state, they would come up with the choice of two states, which are these. At this point, they know that Z operator is being used, but they will still not be able to reconstruct the secret, whether it is 10 or 01, until and unless D decides to provide the information about the qubit he has transformed. If D announces it is the fourth qubit which was transformed, then the parties know that they have the state alpha plus 1 to alpha plus 3, 4, alpha plus 5, 6, and deduce the bit string 0, 1 correspond to Z4. Thus, there are wrong. Thus, they are wrong half of the times. If P1 lies about his measurement, then the correct secret cannot be reconstructed. Dealer uses operator Z1 to send 10. If P1 cheats and measures alpha plus 1, 4 on his qubit, but he makes an announcement as beta plus 1, 4, then participants found the state to be phi which is alpha plus 1 to alpha plus 3 for alpha plus 5, 6 by using the reconstruction steps. They found that operator I1 is used by dealer D. Therefore, the bit string is 00, whereas actual bit string was 10. Hence, the announcement of P1's measurement result is required. Otherwise, the correct operator and hence the correct classical secret will not be reconstructed. If either one of P2 or P3 lies about their measurement result, then the secret cannot be reconstructed. The roles of P2 and P3 are symmetric. Suppose that P2 does not disclose his measurement result, then it is quite clear that the possibility of using any one of the operator is same. Suppose P2 and P1's measurement results are beta plus 35 and alpha plus 14 respectively, but P2 does not reveal his measurement outcome. So in spite of having measurement result of P2 and P3, they conclude the state of the qubit 2-3. Hence, they will not be able to proceed further to reconstruct the secret. These are the conclusion. We have shown that product state using Hadamard basis can be used to split the secret in such a way that the secret can be reconstructed only if all the participants combine their shares to obtain the original secret. But if any one of the participants announces wrong information about their measurement results, or the dealer announces wrong information about the shared product state or the qubit being transformed, then the secret cannot be reconstructed. This suggested technique is innovative since it relies solely on the quantum mechanical features of photon. These are the references. Thank you.
Okay, Priyanka, nice presentation.
Thank you, sir.
Can you measure the complexity of this program?
No, sir. Till now, I have not measured the complexity.
Okay. So, please repeat the security of the system.
Okay, sir.
Okay, Priyanka, is enough?
Yeah.
Okay. Any queries from the audience? Okay, thank you, Priyanka, for your nice presentation.
Thank you, sir.
Okay. Next one.
Sir, we have only 3 presentations. So we are concluding this session here. Tomorrow we will have 2 sessions. By 5:30 we will have a talk by Dr. Lakshmi KV from Amrita Institute. And the next session 2 will be by Lexi Alexander from DRDO. So all the participants, please do join on time. The link will be shared through to your WhatsApp group. Thank you. Good night, all. Thank you, Saju sir. Thank you, Dr. Saju MI, for sharing this session.
Okay.